Let's start at the very beginning. Consider an arm-shaped body whose center of mass is located close to its distal end. If an impulsive force is applied perpendicular to its longitudinal axis, along a line that passes through its center of mass, the body moves in a pure translation. Its center of mass moves in a straight path in accordance with Newton's first law. However, if the impulse is applied on the center of percussion, the body moves in a general plane motion. The center of percussion is described as the point on an extended massive object, attached to a pivot where a perpendicular impact will produce no reactive shock at the pivot. In the general plane motion, the center of mass of the body moves in a straight path and the body rotates around the center of mass. A point to note is that the force, perpendicular to the geometric axis of the body, applied on its center of percussion will produce no reaction at the proximal end. This is well known in baseball. If the ball hits the bat at its center of percussion and the batter's hands are at the pivot point, the batter feels no sudden reactive force. Now consider that the first body is connected to a second body. An inertial conflict is established. To move in a straight path, the first body, when acted upon by an impulsive force, has to cause the motion of the second body. However, the second body, being initially at rest, has the property to maintain this state, and acts upon the first body to cause its rotation around the interconnection, and its center of mass to follow a circular path. This means that, in each case, one of the inertial tendencies of the two bodies is thwarted. This process is being called, in this channel, inertial confrontation, that results in thwarting the inertial tendencies of the two bodies in dynamic interaction. The concept of inertial confrontation, and its result, is directly connected with Newton's third law of motion. Taking into account its property, if an impulsive force is applied on the center of percussion, it does not produce a reaction on the pivot or interconnection. When the impulsive force is removed, the system is free of external forces, and the interaction between the two bodies is restricted to their conflicting inertial tendencies. As a result of this inertial confrontation, which implies thwarting the inertial tendencies of the interacting bodies, it is observed the rotation of the center of mass of the first body around the pivot, and the forward motion of the second body. It should be noted that the motion of the second body is not caused directly by the external impulsive force applied on the center of percussion of the first body, because it produces no effect on the pivot. The first task is to explain the motion of the second body resulting from this conflicting interaction, in accordance with Newton's third law. The established and popular explanation is that the motion of the second body is caused by a centrifugal force, manifested by the first body during its unbalanced rotation around the pivot. There are two problems with this argument. First, the centrifugal force simply does not exist because a body cannot manifest a force upon itself. Second, Newton's third law is violated. Since no exception to the laws of motion has yet been found, a new explanation has to be provided. To do this, it can be noted that, for an observer at a fixed distance from the original position of the pivot, at the start of the process, the path followed by the center of mass of the first body is not circular, but a curve located between the straight path in which it would move if it had inertial unilateral dominance, and a semicircular curve in which it would move if the second body had inertial unilateral dominance. This intermediate curved path, followed by the center of mass of the first body, represents thwarting the inertial property of the two interacting bodies. As a result, both the backward bending of the path of the first body and the forward motion of second body can only be caused by mutually opposite actions. These actions result from the thwarting of the inertial resistances of the bodies to acceleration manifested upon each other as forces. In other words, it is the inertial resistance of the second body to forward acceleration that causes the backward bending of the path of the center of mass of the first body. Reciprocally, it is the inertial resistance of the first body to move in the backward curved path that causes the forward acceleration of the second body. This description allows the understanding of the conformity of the forward displacement of the second body, simultaneous with the unbalanced rotation of the first body with Newton's laws of motion. It is concluded, experimentally, that action and reaction, in Newton's third law, have to be simultaneous and not sequential. Now consider a device composed by an arm-shaped body, or first body, with its ring-shaped proximal end mounted on a vertical shaft, fixed to a wheeled base plate, or second body. The vertical shaft is the center of rotation of the first body in a fixed angle that could be of about 90 degrees. When the first body is momentarily at the sides of the angle, impulsive forces are applied on its center of percussion. As seen earlier, in the short time interval in which the impulsive forces are applied on the first body, there is no reactive force on the pivot. Therefore, the external impulsive forces have only the effect of stopping and accelerating the first body. That moves with the property to follow a straight path while rotating around the pivot. The motion of the second body occurs while the first body is rotating around the pivot and is independent of the direct effect of the external applied impulsive force. From what was seen previously, the inertial resistance of the first body to move in a backward curved path is in conflict with the inertial resistance of the second body to move forward, since it can be anticipated for certain that the forward motion of the system has to be in accordance with Newton's third law. The concept of centrifugal force associated with the unbalanced rotation of the first body around the pivot has to be replaced by the concept of inertial confrontation. To explain in more detail, when the impulse is removed, the first body moves with the inertial property to follow a straight path. However, this would cause a large forward acceleration of the second body that resists and inertially acts upon the center of mass of the first body as a centripetal force to cause the backward bending of its path. Action. Since the first body resists this backward bending of its path, which means a backward acceleration, this inertial resistance, manifested upon the center of mass of the second body as a force, causes its forward acceleration. Reaction. The forward motion of the system is divided in pulses, and in each pulse, Newton's third law is applied as expected. The resulting acceleration in high frequency can be felt as almost continuous, with the forward motion of the system resulting from the unbalanced rotations of the first body explained with Newton's third law. The challenge is to obtain a mechanical arrangement capable to be put to practical use. A mechanical design for this purpose has to deal with the rebounds of the first body at the sides of the angle of rotation, without causing a backward force on the pivot that would make the system an oscillator. The first step is to employ a second, symmetric counter-rotating body. It is now easily seen that, if two equal impulsive forces, perpendicular to the geometric axis of the two bodies, are applied on their centers of percussion, their centers of mass will move in straight paths while rotating around the pivot. However, when this device is installed on a wheeled base plate, let's call it body C, an inertial confrontation takes place due to the conflicting inertial properties of the bodies. The paths followed by the rotating bodies are backward curved due to the inertial resistance of the wheeled base to acceleration. That is thwarted and, consequently, accelerated forward because the counter-rotating bodies resist the backward bending of their paths. As described in other videos, kinetic energy is transferred in the process from the rotating bodies to the wheeled base. However, this simple arrangement raises problems. First, how to apply impulses on the symmetric bodies and, consequently, deal with rebounds to reverse the directions of rotation without applying backward reaction forces on the wheeled base. As stated by Newton's third law, the two applied impulsive forces have their equal and opposite reaction pairs. We are employing here Newton's third law linear to put the two bodies in motion around the pivot. Of course, this is useless for an intended design. To avoid external reactions, we must imply Newton's third law for rotation, since the motion of the two bodies can be seen at a first glance as rotations around the pivot, and this is useful because, regardless of the way in which they are set in motion, they will always maintain the property to move in a straight path, as defined by Newton's first law, as if they are set in motion by a linear process. This means that we can use angular impulses instead of linear ones. With this possibility in mind, we can consider the two remaining problems towards a desired configuration. Starting with the rebounds, to reverse the direction of rotation, an obvious way is to employ springs to stop and accelerate the bodies. Since the springs cannot be fixed to the wheeled base, the rebounds must occur between the two rotating bodies. Modifying the geometry of the second body, the springs are fixed to side extensions, separated by an angular distance relative to the pivot, taking into account the expected angle of rotation of the centers of mass of the bodies. In this modified configuration, let's call the bodies, respectively, first body A and second body B. Considering that the utmost condition for this arrangement is to avoid backward forces on the pivot, an appropriate geometry of the two bodies and positioning of their centers of mass are mandatory. Finally, it remains the problem of maintaining the opposite rotations of the bodies A and B around the pivot. The chosen option for this task was an arc electric motor, whose primary is fixed to the proximal end of the first body, A, and the secondary fixed on the upper face of the modified semicircle-shaped body, B. The device is composed of two counter-rotating bodies, and, to avoid remaining backward pulses, should be connected to the wheeled base by an appropriate connection mechanism. These explanations and arguments are expected to provide additional inspiration for enthusiasts in the matter.